Swayam Prabha. Digital India. Educated India.
I'm really very happy and honored to have been invited in framework this GIAN initiative. And I have also learned that besides meaning a global initiative of academic network, the word GIAN has also a meaning in Hindi. So really very honored to be part of this initiative. As Professor Radhakrishna said, it's for me also a personal pleasure because I have many colleagues and friends here. This is my 10th visit to IIT Madras starting from 2008. So I feel more or less quite at home when I come back here. And as a matter of fact, I've tried to bring here more or less a part of the class on precast structures that I teach at the Master of Class students in civil engineering at Politecnico di Milano. And well, also following with the slides that we have seen, the lecture of the previous hour. First of all, we should ask ourselves, why are we going to precast? Well, as a matter of fact, we know that precast concrete construction has several benefits, which goes from, well, here it's written economic. These words are taken from the handbook on precast concrete structures of the FIB, the International Federation of Concrete. Well, economic, I will say better cost effective, because sometimes economic might mean, or might you misunderstand that you're just saving money. No, you must be cost effective. You have to put money where they need to be put and avoid that money goes into, some streams that you don't control and their waste. Then we have durability. This is a very important concept that we have to keep in mind wherever we construct. It is structurally sound because, as we have seen also from several examples beforehand, you can really design and make a structure to perform in the best way for that application. Architecturally versatile. So what is precasting? What is prefabrication? Well, it's bringing industrialization into the construction process, into the construction practice. But let us not make the mistake to see prefabrication as a different way of making something that we can do with cast in situ. So we should not regard simply the fact that we bring off-site something that generally we are used to perform on the site. Otherwise, we are driven into something which does not fully exploit and does not fully recognize the benefits of precast construction. And as we have learned beforehand, we must approach the whole problem from a holistic point of view, because we have a construction system with its own characteristics, and this governs the layout, the spans, the assembly, the stability of the system, and so on. So really, this has to be taken into account from the very onset of the design, from the very concept of the design. And it's very important to do that. And so the issue is, okay, but sometimes, well, the first class, I ask my students why did they choose to attend the class on precast concrete structures, and then I explain them why in the educational offer of Politecnico di Milano, of the Civil Engineering Master of Science program, we have decided to put a class specifically on precast concrete structures. What is there that you cannot learn or you don't learn in a class on reinforced concrete design. What is specific? Well, and as a matter of fact, it's in a way the way of thinking. It's the same thing why do we have a class on concrete structure and on steel structures? Because it's not only the material that behaves differently, but it's because the design is governed by different principles, for example. Generally speaking, when we design a cast-in-place reinforced concrete structures, we can rest assured of the fact that if we detail well the reinforcement, the connection, and so on, the structure is monolithic because we cast it together. In steel structures, this is not. We have joints, we have connections. Then steel structural elements are made in such a way that the deformability issue, the serviceability limit state issues, or the stability issues govern the design rather than the strength. Whereas in reinforced concrete structures, at least in ordinary reinforced concrete structures with ordinary concrete, we first design for strength and then we check the serviceability, which in most of the cases it's guaranteed. Well, in precast structures is the opposite. Why? Well, because with precast structures, exploiting better quality control of the material, the possibility to produce with reliability better strength concrete, exploiting the pre-stressing, we can go to spans which are 4 times larger than, which can be up to 4 times larger than the ones that we use in cast-in-place structures. We can have more slender cross-sections, so stability issues become much more relevant than they are in ordinary reinforced concrete design. We have concentrated stability problems. The classical case of a column with a point load which moves is a typical case of a column in a precast frame. We will see it during the classes of next week. Well, in reinforced concrete structures, we assume the nodes to be rigid. How does we transfer this assumption? How can we transfer this assumption? Or how do we have to modify this assumption when we go to precast structures where we do assembly, for example, with steel carpentry and so on, we do assembly the elements. And then, as we also learned in the previous lecture, during its construction stages, the structure experiences situations in which it behaves completely differently than when it's completed and fully in service. So when it's completed, you can have a 3D scheme with some redundancy, whereas when you go for transport, for example, the beam is simply supported on some forklifts on a truck, just to make an example. And this is a completely different situation, structurally speaking, for your structure. So everything has to start from the conceptual design. Bear in mind that in ordinary cast-in-place reinforced concrete structures, we have generally a 3-dimensional frame, and the stability against horizontal actions is guaranteed by some cores, which are generally the staircase and elevator cores, if you think, for example, of a residential or an office building. In precast structures, you have to adapt this 3D philosophy, because in order to achieve, there are some systems or some countries in which, for example, in the US, in New Zealand, and so on, the main concept for precast concrete structure design is the emulative one. So you have to make the precast structures to behave exactly like a cast-in-place monolithic one. So there is some kind of use of, we call wet connections. You leave some space where the reinforcement goes out and it's connected, and you pour concrete. But that, can result in not fully exploiting, for example, one of the advantages of precast structure, that is the fast execution. So you have to. And so stability in precast concrete structures is one of the issues we have to take care of. And we have to take care of at different levels of the precast concrete structures. For example, we have to ensure that the columns are properly fixed at the foundations. Because most of the cases, the precast columns work as a cantilever. Think of an industrial building, for example, which is one of the most common precast building systems that you can have. The column is a cantilever. So if it's not properly fixed in the foundation, you will lose stability because your system will not be properly constrained. But then you must also have, if you have shear walls for bracing, you must have an appropriate stiffness of these systems. You have to guarantee diagonal bracing or any other kind of resistance versus the lateral actions. And most of all, this is something which is, when we design for ordinary cast-in-place reinforced concrete, we give it for granted. Whenever we have a lateral force, like earthquake, but also wind, one assumption that we make is that the floor diaphragms are infinitely rigid, infinitely stiff in their own planes. This allows us to make a very important, statement in the design that the lateral force is shared by the lateral systems proportionally to the stiffness. Each element takes up a share of the lateral force proportionally to its stiffness. And we have to account also for torsion. Never forget that. But in precast structures, how do we guarantee this? Because sometimes, for example, you see, if we have, there are systems where you can guarantee. But think of an industrial building, for example, where you leave on the roof some, empty spaces that you cover with transparent, sky glasses and so on, because you leave lateral light to come into the workplace. Well, how can you guarantee that the roof system made by structural elements which are separated from each other has the adequate in-plane stiffness? So this is something that goes on into a very strong demand to the connections. And so in the structural design of a precast structural system, we have to design the elements, but we have also to appropriately design in the connection. And going back to an important statement which was made this morning, about contracts, about law responsibilities and so on. In the Italian law, there is a specific statement related to this. Because when you use a precast element, generally a precast factory has its own book with all the type of elements, and for each one of them, they give you some structural design information, what is the maximum load bearing capacity and so on, because those elements have been designed by the structural engineer of the precast factory. But the Italian law states that then, that is one design, but the design of the building, the designer of the building which uses those elements is responsible for how does he use them, or does she use them, in the building. So there are two different kind of responsibilities. It's not that because this is designed by the precast structural engineer, I take it and put it there. Because then I am responsible of how I have assembled this into the building. And this is where the connections play a key role, which is as much important as the one of the structural elements. Well, obviously, precast we have seen also in the previous slides. For example, in Italy, precast construction started with, very ancient form of hollow core slabs or of pre-stressed slabs. We call it swallowtail because they resemble the shape of the bird, for floors in residential buildings. Started there, and then evolved with beams, more for also precast system, then for small bridges, for infrastructure, and so on. So that was, and this was especially in Italy and in Europe after the Second World War, where there was a huge need to reconstruct housing and infrastructure because the country and the continent had been destroyed. There was huge need of fast construction, of industrializing, but not only to go fast, because at a certain point it was realized that also the construction sector needed a level of quality control as other industrial sectors. Needed some kind of the concept of prototyping, because most of the cases were, as structural engineers, we say, well, in our work we make unique objects, and in a sense it's true. There is no building equal to the other, no bridge equal to the other. But with the precast construction concept, we can bring some kind of standardization and prototyping into our work. And this also because, you know, there were other issues. How the construction work the construction industry could take pace with the development in concrete technology. Self-compacting concrete was a great innovation in construction, and it's something that it's now regularly used in precast concrete industry, because the precast concrete industry has the tools to implement the quality control in the mix proportioning, in the mixing and so on, that the self-compacting concrete requires. Also, nowadays we speak about durability, but we also speak about reusability of a building and so on. Well, in a sense, precast concrete construction, precast concrete structures are already conducive to be reused, because, you know, you can dismantle them and you can think. But that brings another legal responsibility issue, because when I have built a structure, as a designer, I have signed it and I had all my quality control procedures. Think that in 30 years from now, somebody else will come because that building is no longer not fit for the purpose, but because the needs of the owner have changed and he wants to reshuffle and so on. So the issue is those elements can be reused, but in which way? Who is going to take the legal responsibility as a designer to take those elements, assess their performance and reuse them? Because he cannot say, oh, I used that because somebody else 30 years ago signed that. So these are things where, you know, it's just an example of how this common framework that has to involve different subjects, institutions, and so on has to be dealt with. And nowadays there are methods of assessing, but there has to be something that you redesign and you take back the responsibility. Well, that is the reason for which, these are some of the reasons for which we decided to, you know, put a course of precast structures in the civil engineering program at Politecnico di Milano, because there are some aspects of innovation that we wanted to be covered in the form of a traditional instruction class, with a warning that, well, we cannot cover everything because innovation goes very fast. And also, you know, the purpose of education, of university education, is not only that you are able to use innovation. If we teach you something, you are able to use that. But we also want to teach you how to drive, how to create innovation, so that if something new comes up, well, okay, it's true, you did not see in your university, but you must be able to cope with it along your continuing education, along your professional work. So what are the opportunities? Let's try to go now deeper into that. What are the opportunities offered by prefabrication? So first of all, we try to bring into construction industry the logic of other industrial sectors. There were that graph that we saw before, the added value per hour worked. Construction industry is often blamed for being one of the least productive and least innovation uptaking sectors in the industry. So precasting is one way, and the one way is that we bring factory-made products with a low number of standardized shapes and dimensions. how they have come up with, where the most common ones, the designer, the architects came together and see, okay, if you want to build a house, these are the most common layouts that it's reasonable to use and so on. Optimum use of materials. And we will see during the classes also of next days, what does this mean? Shorter construction time. Well, continuing erection, because you are off-siting and put into a closed space where you are less sensitive to weather and so on, and quality control. For example, this is a picture I have seen on the program that Saturday some visits are foreseen, but some of you come from the industry, so you know that. This is a precast yard, I would say. You can see here that there are, I don't know if I have, okay, yeah, you see the, okay. For example, here you can see this shape. These are beams that we typically use in industrial beams, double thatched. These are some, I think these are some floor systems in the form of double T's and so on. Well, and which are the opportunities that the factory-made products can offer? Well, first of all, we have rational and efficient production process. They can be very well organized according to the logic of industrial production. Then, as I was saying, we can go up to spans that are 4 times larger than the ones that we use in ordinary reinforced concrete construction, and also having span to depth ratios of the beams which are more efficient. This is because we use pre-stressed concrete, and in precast yard we can use them. I don't know whether here some probably you can see these strands here. Probably these are some of the pre-stressing. You can also see some of them laid out here already with the arrangements which is required by the design. Then we have skilled workers. That is another thing. The quality of the workmanship in concrete construction needs to be elevated, needs to be upgraded. And going for precast construction, this is one of the opportunities. We have a series of repeated actions, and also we can implement automation as it's nowadays a trend in industry. And these are some other examples. You see, this is one of those, double-touched beams that you are seeing. This is a mixed-use building for offices and so on. So at this top floor, as you can see, you needed also for, representative purposes of the company having offices here. You need open space to host meetings and so on. So the span changed. You need an open space here without intermediate columns, whereas at the bottom floors you have a different arrangements. And the other thing is that, well, here it's a little bit blurred, but how did precast industry uptook the concrete technology innovation? When in the 50s, I would say, all started, or at least in Italy, in Europe, there was this boom of the construction market because of the reconstruction post-war needs. The concrete strength was, well, hopefully was a C25. Well, consider that C25, it's already quite a good concrete, because C25 means that the characteristic strength on cylinders is 25 megapascal. This means on cubes, the characteristic strength should be 30. But characteristic, average, if you measure it on cubes, you have to add up at least 10 megapascal, more or less average. So it means a C25 concrete means that you have an average on cubes of 40 megapascal. It is quite a good concrete to be produced on site. But then the technology evolved. Now, if you take, for example, the Euro code or the FIB model code, you can use, there are up to class C100, 110, or even up to C120. Very high strength concrete, ultra high strength concrete and so on. But this means very, very precise quality control. Also, in precast concrete, you can rationally handle it the seasonal variations, because casting in summer is not the same thing as casting in winter and so on. So this is something that in precast concrete industry you deal with. And the other thing is, let's think always in an engineering way, engineering-wise. It's true that if you want to have a better strength concrete, let's say simply better strength, you must use a higher quantity, not only, but among the mixed design characteristics, you must have higher binder content. You cannot have a better strength concrete without using a higher binder. But it's not the only thing. To have a higher strength concrete, you also use different mixed design methodologies. You go to aggregate packing concepts, you use admixtures and so on. So do not look only at the left-hand part of this slide where you see the binder consumption versus the strength. Because if you read only that, you always end up saying, okay, a higher strength concrete is less sustainable, because where does the most of the carbon footprint of concrete comes from the binder, and the binder must be at least in a certain part cement. Not because I do not believe in alternative binders like geopolymers and so on, but simply because we do not have enough supply of those alternative binders. And to meet the demand of concrete, at least we need to have cement. But as I said, when we design a higher strength concrete, we use different mixed design methodologies. So if you look at this right part of the graph, you see here there is not only the binder consumption in kilos per cubic meter, but it's a sort of binder dosage per strength unit. And so you see that the binder intensity becomes more effective when you go for higher strength, because you extract more strength from that binder dosage. And this is something that with the framework of precast construction, with the quality control in the production of the concrete, you have. And there is another thing. By law, each precaster must daily control the strength, at least the strength of its concrete. So concrete factories have a unique database for controlling the quality of their concrete. And nowadays, with this artificial intelligence tool and so on, it's easy also for students like you to write a script in Python to enable, something like that. This is very unique. You do not have this in ordinary cast-in-place concrete structures, because there you have different laws, different countries, but you must make a minimum number of checks. You must take some cubes and keep close to the structure and then bring to the lab at 28 days. In precast concrete, you check the strength. Depending on the application, you check the day after. If you have pre-stressing, when you release the pre-stressing, you have to check the strength to see if it's compliant, and then you check at 28 days. So this allows you to have your own statistics of your own concrete and to go for quality control. And then, I don't know whether this is, no, this was supposed to be a movie, but it's okay. Yeah. One of the most important innovation in precast concrete industry was self-compacting concrete, a concrete which does not need vibration. What does this mean? Well, it means less noise in the yard. And this is important because, okay, we go to visit the factory one day and then we go back to our office. It's a very nice place. But think of the workers which daily stay there. So one of the SDGs that we were saying before was also health and well-being of workers that are not exposed to noise. When you go to vibrate with the poke vibrator and so on, one of the pathologies that construction workers suffer is dead fingers, because this alters your circulation. So if you reduce the vibration, that turns out into a better health for the workers. But also self-compacting concrete, which deaerates, which consolidates, you can have a better finishing. you can also have not, well, self-compacting concrete contains more fines, so you can produce more reliably a better strength concrete. But what you can have is also a less dispersed performance of the material. There is one question mark: the pressure on the formwork. As we said before, formworks have to be designed. Well, there are models, we will see them tomorrow, but self-compacting concrete is a fluid, and as a fluid you should design the formworks for hydrostatic pressure. This means that probably some formworks should be over-designed with respect to other kind of application, but there have been, technology developments to help with that. But an important thing that we have not to, forget is always that we have to take care of the formwork. Also because even in cast-in-place construction, formworks can be an important cost item. That when we think of how much do I pay for concrete, yeah, for concrete is one thing, for steel is another thing, but formwork are another important cost item that in cast-in-place construction, sometimes you cannot use them more than a few times, whereas in precast industry, you can design, you have steel formwork and so on. You can also optimize that issue as well. And I don't know whether here there is the movie, no. Okay, well, this was an example of how a self-compacting concrete was cast on the site. Well, you see here, some designs of the formwork. You see here that this was a, you can see that it's more or less a 3-meter high wall. So not that very, very high, but you see that there were some, transversal reinforcement to the formwork exactly because there was the need to adequately counteract the hydrostatic pressure of the concrete. Well, better finishing or also having the possibility to cast some not so conventional shapes. You can see here these are circular columns for a 2-story building, because you can see here there are at this position here and this position here, these kind of corbels, which were designed then to accommodate the horizontal part of the structure. And the other thing is that, for example, dealing with quality control and so on, when you cast columns in prefabrication, you cast them horizontally. Then you have to transport, and then you have to tilt them up, and there is the design of this tilting process. But it's an important thing, the horizontal casting, which guarantees the quality in the position on the reinforcement, especially the transverse reinforcement. I had an experience to tell about this. We were working in a European project, so things were managed pretty well, because there was. And the structure was built for research purpose, okay? We had 5-meter high columns, which were cast with the pump from the top. The stirrups, it was designed for earthquake testing, so there was quite some tight stirrup spacing, at least at the bottom and at the top of the column. And they were tighted, but the force of the concrete falling up from 5 meters, in some cases displaced the stirrups, even if everything was done correctly. They moved, and so we had some, unintended failure mode because the stirrup spacing was not maintained during the casting. When you cast horizontally, it's first of all much more easy to control it because you inspect that in line, but also you do not have this risk of displacing just because of the falling force of the concrete, which is poor. And another important innovation that precast concrete industry was able to bring, it started really from a precise need of the precast industry, was fiber reinforced concrete. Well, I can tell you the Italian experience, but the same was also in US. How did it go into the ACI 318 code, which is the structural design code? We will see some of the widest produced precast elements in Italy and Europe are the elements for roofs, which can be in simple shape like double T's, or can come in folded plates, shells, and so on. In that case, putting the transverse reinforcement into very thin elements, because one of the benefits that you can have very thin elements, while putting the steel roofs or some kind of shear reinforcement sometimes can be very complicated. So the companies were eager to replace those steel roofs and so on with fibers. Also because they, well, you can say, but you pay for the steel of the welded wire meshes and so on. You pay for the steel of the fibers. Fibers are also a little bit more expensive. So. Yes, but you saving the workmanship for detailing, which can be a long process. You need quality control. Another important thing, you save the space for storing the welded wire meshes and for storing them when they are formed and so on, because fibers come into bags and you just need another silo in your batching plant. So space is also an important thing to take into account in managing precast concrete. Well, so fibers can help also in solving the problems of some intricate details, intricate reinforcement details, where you can get into so complicated things that your vibrator cannot go on. So fibers can help into that. And also they enhance the toughness of the material, the flexural toughness. You will see, you will have a class on materials. Generally, fibers do not increase the strength. A fiber reinforced concrete has not a higher compressive strength than its parent concrete, and the fiber reinforced concrete has not a higher tensile strength. What it does have is that it has higher post-cracking toughness. Whereas plain concrete, after cracking, it goes down, and so we neglect the tensile properties of concrete in the structural design. When we design a reinforced concrete element, we say concrete in tension, it's like if non-existent. It just stays there to connect the compressed part of concrete and the bars and to guarantee that they work in a composite way. In fiber reinforced concrete, that material in tension, we use it in the structural design. So you can also, imagine that this is also something in favor of sustainability. You have some material there, you are using it. Okay. And they also control the cracking. Controlling the cracking means that you can, first of all, deal with issues like shrinkage, restrained shrinkage, temperature variation, and so on. But also you can have a better durability, because a narrower crack means narrower penetrability to whatever kind of aggressive agents you can have. And bringing fiber reinforced concrete into the structural design codes was a long time journey, because it started more than, I think, 30 years ago. Professor Ghetto, for example, was heavily involved in this in the European and international work. And nowadays we have design rules, because, whenever we have an innovation, in order to fully exploit it in the concrete construction industry, we must bring it into standard and codes. Otherwise, you can say it's a benefit, it's a plus, but how do I evaluate it? How do I assess it? So this is another important thing. And well, this was also, there was a movie here, but this is, sorry that it does not work. This is an automated tool to detail the reinforcement, but it's something which can be as large as from here to here. So you need space to do that, whereas with fiber reinforcement, you can save this. See, these are some examples of how do you have to shape the reinforcement. This is, can you imagine what this is for? It's a tunnel liner, yeah. It's a segmental tunnel lining. Well, tunnel linings are one example of structures where not only prefabrication has give a great speed to that, but also where fiber reinforced concrete is the material to be, because the tunnel lining is a closed ring and it works mainly in compression. there can be some bending moments and so on, but the tensile is very low. So it's where fibers can really help. And I have a lecture specifically onto that because, well, tunnel lining, it's everything okay when you have formed the closed ring for the lining, but then you have to cast, you have to lift, you have to transport. There are different, transient design stages where it behaves in a completely different way than the closed ring. And this is an example of, where it all started from, at least for me. I started working on this project when I just graduated from PhD, so I was more than 25 years old. This is a roof element, and it's made in the shape of a bird with open wings. A famous car designer designed that shape. So there was a factory who wanted an Archistar for its signature building, so they call it this very famous designer for sport cars and so on. So he designed this roof element in the shape of some wings. And, well, you see in this, there are some, bulbs here. This is some where you have the longitudinal pre-stressing tendon. So the main static behavior to work as a simply supported beam is guaranteed by that. But the other thing is that these two wings, imagine, these two wings work as cantilevers. And when you install this side by side, for example, what you can have here is that here you lay out a roofing, sky roof. So you have some concentrated forces exactly acting here. So that cantilever is subjected to a point load at its free edge. So you have negative bending moment here where this cantilever wing frames into the main bulb. Negative moment, what does it mean? It means that you need reinforcement on the top. That is. So think that, okay, you need at least 2 centimeter cover. It's true that then these elements come with some kind of waterproofing. You can have thermal insulation. So the concrete is never directly exposed, but you have to give at least 2 centimeter cover because that is the minimum. Also for tolerances, because if you give less, you risk to have even less. 2 centimeters, then you have the reinforcement, which is at least 8 millimeters, so you have another centimeter. And then you need to give some distance from the neutral axis, otherwise your bending action is not guaranteed. So you end up with a thickness of that wing, which has to be at least 10 centimeters. Then you can decrease it a little bit toward the edge. But average, it was about 8, not less, 8 centimeter thickness. 8 centimeters means 200 kilos per square meter on the top. Just to make a rough. What is, well, okay, you say, okay, I know this, 200 kilos, I designed for that. But the issue is that in an industrial building, mostly one story, that is more or less the only or the largest part of the mass. It's on the top, it's on the roof. And Italy is an earthquake-sensitive country. So this means that you have your cantilever column with a big mass on the top. You have what we call an inverted pendulum, which is, from the earthquake point of view, the worst case that you can design. So reducing the dead load of this element meant that we could have cascade effects also on the design of the wall structure and of the foundations as well. So the company said, why don't we use fiber reinforced concrete? Because we can avoid the cover and reduce the thickness. We can. Perfect. But it's never so easy. We made with fiber reinforced concrete, and we made, I will probably show some slides, some pictures later, we made some full load test on the wall element. It was a 15-meter long element. This is another important thing in precast structures. You have also to check not only your concrete, you have to make load tests on your elements. So in this way, you also check how your design is reliable. That is a very important fact that we can have in precast structure. We have, when we tested this element, we had an unexpected failure of the wings. things. So we started saying why? And then we had the idea, okay, let's take some cores. And we had at that time in the aerospace engineering lab some small X-ray facilities. Because I did also when I was doing my PhD, but I went to a veterinary clinic in the night. Veterinary clinic because of health issues. You cannot bring concrete into an X-ray facilities, which is used by humans during. Veterinary clinic was okay in the night because in the day they were the animals that have to be taken care of. And we made the X-rays on the cores. Imagine that we have a 10 centimeter more or less thick core. We cut it into half. This part here is the top. Do you see any fibers? This part here is the bottom. What did happen? We need to vibrate, and vibration led to settlement of the fibers. But since this is a cantilever and we have the moment which is negative, we need reinforcement on the top, this vanified all our efforts. So that was why we went into self-compacting fiber-reinforced concrete, which avoided vibration, and this was the same core made with self-compacting FRC. This is the top, this is the bottom, so we were able to guarantee this. So one interesting thing was that with self-compacting fiber-reinforced concrete, we avoided the vibration, we had better fiber dispersion. But there is another advantage that you can have with self-compacting fiber-reinforced concrete. Especially when you cast long elements, you can drive the fibers along the flow. And if you have designed your element and you know where your tensile stresses will be, this means that you can control the alignment of the fiber. And this is due to a simple fluid mechanics principle. So the nice thing that when you deal with, materials in precast construction, that you can bring also some interdisciplinarity. So I had to go to my fluid mechanics handbook when we dealt with this problem. When you cast concrete, imagine that you have a free surface flow, okay? And if it will be a Newtonian fluid, which concrete is not, you have this, and you have this distribution of the stresses inside the concrete, of the shear stresses, which are those with dry flow. Shear stresses are maximum at the interface with the mold because there is friction, and are zero on the top because it's a free surface. If the fluid is Newtonian, what does it mean? It means that you have a linear relationship between the stress and the strain rate. And the proportionality constant is what we call the viscosity of the fluid. So if the stress distribution is linear, you have strain distribution which is linear. If you integrate the strain distribution, you have the velocity profile. And the drag forces are proportional to the square of the velocity. So this force, this profile here is the profile of the velocity. And it means that the resultant of these forces is more or less on the top. So if you have a fiber which is crosswise the flow, you can tilt it and align it with the flow. When you have ordinary concrete has a very high, what we call in rheology, is the yield stress. It's a level of stress that you have to overcome in order to initiate the flow. So until your stress reaches this value, tau 0, you have no movement, you have zero strain rate. It's the case, it also happens when you have pumping. You have this plug. So you rigidly displace, you rigidly shift the part of the concrete which is not sheared, and the sheared part drives in. But this means that the resultant of your force is no longer close to the top, it comes back close to the middle. So you also rigidly displace the fibers. When you go for SCC, you have a low yield stress and a balanced viscosity fluid. So you limit your plug flow zone to the very top, and you also have a high gradient so that your forces are, in such a way that they can align the fibers along the flow. So this is the mechanism which is behind the fiber dispersion, fiber orientation controlled in self-compacting fiber-reinforced concrete, which you can effectively use in precast construction. Then you can have, as I was saying, going back to the benefits of concrete construction, shorter construction times. Even in winter, you can, because you cast off site and you can bring it. And this means that you have a faster return on investment. That is an important parameter to judge this. And also the benefits I was saying before. In every precast yard, you have to daily control your strength. But not only at 28 days as you are obliged to do for cast-in-place concrete, but also, for example, if you are using for pre-stressing operations, you test the morning after casting. Pre-stressing normally occurs at 16 hours, conventionally we say. These are data from 3-year-long production in a precast factory in Italy. And you see another important thing is that you can clearly appreciate here. You see this at 16 hours, they had, strength about 30, 35, 36, 40 megapascal. But with SCC, this compares normal vibrated concrete to SCC. You see the FCC was gaining strength faster. You have a higher number of samples in the region where you needed that strength. And then you have at 7 days, at 28 days, and so on. But what you can also appreciate here, you see that this curve, first of all, you appreciate that the distribution of the strength in concrete is not normal, but can be something log normal. But the other thing you see here that you have, because of the better quality control, the tail, if you imagine to draw the continuous, the Gaussian or whatever it is, the tail of that curve is shifted towards the higher values. So it means that you have better reliability of your material properties that you are going to use in the design. These are some other examples. These are the strength at 28 days, which follow a similar pattern. The other thing, as I was saying, is that you do not only test the concrete, but you can, and you have to in some cases, test the element as a wall. This is a precast slab made for bridge decks. This was an Irish precaster with whom we worked also in the framework of a European project. Well, they did, for example, most of the facilities for the London 2012 Olympics. And now one of their most recent works, I visited, it was already 3 years ago, is the third tunnel in London under the Thames River, which solved huge traffic congestion because of the commuting people and so on. That was all made with precast concrete segments with this precaster provided. And we tested this material. You saw there is this frame, which is a contrast frame, and this is the jack which applies the load. This was made with basalt tendons for precasting. And you can see here that you can appreciate the deformation because basalt tendons have a very high limit of elasticity, and they can also have some, bring back effect. You can see this very, very wide distributed cracking. There were fibers also into that with guaranteed. One of the drawbacks of basalt tendons, because you can say, well, they are very interesting products because they do not corrode. So they can have a better durability. The issue is that they are brittle. And, one issue that had to be solved was that the same grips that you use for steel tendons cannot be used for basalt because you crush them and you risk to break them when they are still, bare and waiting for the concrete to be poured. So this is a further stage that you have to take into account. And these are some examples of the load testing that we made in the factory. You see, you can appreciate this shape of the winged elements. Well, as a matter of fact, when you go for very long spans and so on, you might not have, or the company might not have a fixed contrast frame for testing. So the usual way to apply the load is that you go with the bundles of steel bars. And why do we use them? It's because they come with a certified weight. So they have officially labels and so on, so you know exactly the weight that you are putting on your load, and you can replicate the load sequence. So what are the further advantages that we can have with precast concrete construction? Yes. Yeah, well, actually, the bundle is 12 meter long. Okay, so you put, for example, you put here. We took record of the sequence. I have some slides where you put the first, where you put the second. So, for example, we put the first in the middle, then we put the second here. So you start having some, also torsional effect, and then you put the third to balance it, and you fill it up until when it collapses. In this case, we needed two of them because the span of the element was more than 12 meters. What? It's like applying a distributed load, yeah. It's like applying a distributed load, like a line load, yeah. Okay, yeah, as I was saying, the further benefits could be, first of all, that because of the better finishing, but also because, you can design your formwork, engineer the design of your formwork, use your formwork. You can have also good architectural values, good shapes, structural efficiency, we will see, flexibility, adaptability, fire resistance, and environmentally friendliness. For example, this is a stadium. Yeah, you see also the Chennai stadium was mentioned before. You can employ this also in this case. And this is, this is an office buildings in the north part of Milan. We call it the Pineapple Building because it's like that. And, there is some, here you have, the top of it, you have skylight, so the offices take the natural light directly from vertical lighting, zenithal lighting, as we call it. This is a quite famous. This is a church in Rome. Was built for the 2000 Jubilee, so now it's more than 25 years in service. Which was the particular issue of this structure? Well, in the shape of some sails, boat sails, but the issue is that this concrete was made with nano titanium dioxide, which is a photocatalytic material. Under the sunlight, it absorbs the CO2, it absorbs the smog, it was self-cleaning and so on. So it was also a way to bring material innovation into that. And also some examples. It's not necessarily that you build structures. You can also build artworks with this. The other thing is that since, as we said, we can have, beams with longer spans, we can use higher strength concrete, so we can make more slender columns. First of all, we reduce the volume of material that we employ. But after that, we can have larger free open spaces, which for the readaptability of the building space, it's better. And these are some other examples that you can see. Well, some pictures are blurred. You see here we have some internal cores, but the rest is almost free space. Well, this is not very clear as a picture, but is an example of how a precast building can be not only structurally, but also energetically retrofitted. Because you have this facade, most of the cases, the facades, if they were built in the 50s, there was no thinking at all about the energy efficiency. And nowadays, with climate change, we have also in Italy, we are changing our paradigm. It's not only that we have to heat our buildings during winter, but most of the energy that we spend into that is to cooling them during summer. So you need very energetically efficient facades. So if you are in precast construction, you can simply remove the old facade and apply a new one which has different energy concepts. Whereas in traditional construction, nowadays one of the most common employed technologies is what we call the coat. You simply apply an overcoat on the outside. But that means, because outside, why outside? Because if you apply from inside, you reduce the free space in your apartment. And nobody, if you go to a condo, to an apartment building, and start asking the people there, they say, no, I don't want anything to be touched. But there is sometimes also that it's happening now in the apartment building where I live. They also say, no, I do not want anything outside because I lose 10 centimeters on my balcony. Well, you have to lose something somewhere, because otherwise you cannot retrofit energetically your building. And you can say this. Another thing that you can have with precast construction is that you can combine different materials. So this is an example where the supporting structure is mainly steel, or you have also, you can see some bracings which are in steel, and you combine with precast floors. This is another example where you have these timber joists combined with these predal systems made of precast concrete. And this means that, you know, all converges towards using less raw materials, using less energy, recycling the production waste. It's quite common, for example, that the water which is used for washing the casting equipment, it's recycled in the production of concrete. Well, there are studies on that, because that water contains slurries and so on. So when you add as a water, it's not only water. But you solve an environmental problem, because otherwise that water containing cement, containing alkaline materials, has to be treated as a special waste. So it will be difficult to handle it, or it requires special care. And another thing is that as you have a database for the performance of the material, in the precast concrete construction, now you already have a database for life cycle analysis, which is something that we need to perform. So this is another important aspect. Also this one here is, how do you recycle it? In a plant, you recycled some, the aggregates coming from washing the concrete material, and this is the principle of circular economy. But as a matter of fact, the picture is quite blurry. Specific issue. What time shall I finish at? 12? Okay, and no, I still have my watch. Okay, I have 20 minutes. I have my watch on the Italian time still. Yeah, okay. Another issue, as I was saying before, and we will dedicate a specific class on that. How do we guarantee the stability of a precast building system for lateral forces? And well, here is an example of how, for example, lateral forces due to wind come. You have the wind coming from this direction here. So you have wind pressure on this side of the building, but you have wind suction on the other side of the building. And also, because of turbulence, you have this airflow, and when the airflow hits the building, the current has to deviate and then has to reconverge. So there is some turbulence here, which creates suction, but there is some turbulence also here, which creates the suction as well. Well, these two lateral wind suctions, for the global stability, they are self-equilibrated, because we can assume that they are equal and opposite. But still, you have to design the elements for local suction. You have to design the connection of the panels so that they are not torn out. But this suction here brings the two issues, brings the issue of local stability, but also the issues of global stability. And if we want to keep, for example, the benefit of having in precast structures large spaces, think of an industrial building. You cannot put a bracing in the middle of the building, because otherwise you are designing a precast building to host a precast factory, like that. Your precast beds should not be interrupted. Otherwise, your bridge crane, which moves the bucket with the concrete, cannot move. So you have to assign this lateral load resisting action to elements which are, posed on the perimeter of your building. Can be shear walls, can be staircase cores, and so on. And the issue is, as I was saying before, first of all, how do we guarantee the diaphragm action of a floor deck or of a roof deck, which can be discontinuous? The other thing, since we might have different elements, how do we distribute the forces among the different elements? And consider also that lateral forces are not only forces. In this case, the force is here, but the center of stiffness of the building is more or less shifted. So you can have some torsion effect. How do you calculate this torsional effect? How do you distribute these torsional effects among the different elements? You can see here, this is a typical precast frame. And you can have forces, horizontal forces here, but these corbels here that I'm pointing out with the arrow, these corbels here, they generally host a bridge crane. Okay? And bridge crane transmits gravity forces, vertical forces, but because of eccentricity or because of the braking forces, it also transmits horizontal forces. And for these horizontal forces, you have to design the corbel, and the corbel is not a beam element in the sense of the Bernoulli theory. It has to be designed with a strut and tie mechanism. But also you have these local forces which bring some moments, some flexural effects on the column, concentrated flexural effects for which you have to design. And these have to be brought down to the foundation, and you have to guarantee the stability of that as well. And these are some examples, some elements. You see, for example, this is a layout. It's an architectural drawing from a two-story building. These were typical. Now they are not so much common. They were typical foundation element. They were precast as well. Well, they were very effective. You brought them, you installed the column inside, you put the column inside, there was some centering mechanism to help, there was a pin, and then you completed pouring, generally with shrinkage compensated concrete. So this was very effective in guaranteeing the fixed edge at the bottom of the column. Why they are not so more common? Because over time, the earthquake design requirements in Italy and in Europe changed. And nowadays, we apply what is called the capacity design to the earthquake design of buildings. So you don't design the foundation for the forces and bending moments which come from your structural analysis, but you have to design your foundation to be more resistant than what your columns are, because that is the last element to fail, that has to fail. So you have to apply an over-design factor to the resistance of the column and use that as a design action for the foundation element. Some cases it comes out to be very, very big and unpractical. And also, one of the drawbacks of having this isolated foundation is that if one settles, you do not redistribute the action. So you have to provide like continuity connection beams between the foundation elements. So nowadays, at least in buildings like commercial halls or industrial buildings, the common practice in Italy is that you cast a continuous foundation and you have connections that connect the column to this continuous foundation, and you have to design them. I will show you a design example that we worked on. You have to guarantee that connection guarantees the clamping action and a certain level of over design for the seismic action. These are other typical elements for precasting. Actually, this picture, this brings me back also to a consideration, a concept which emerged, the standardization. So we have in Europe a EN standard for precast roof elements, and they were categorized according to those 6 categories. Can you guess which was the criterion which dictated the differentiation into categories. Well, for this last one, yes. For the what is F1, yes. The categorization was based on the mechanism of resistance to torsion. Because here, this kind of element here, where you have a core, that is the best way to resist to torsion, because you have a hollow cross-section. These elements here resist versus what we call the biflexural mechanism. And also these, you know, U or omega-shaped element, even if it's less effective than here. These elements here, the so-called star elements, they are very bad in resisting to torsion, because they only have we call the primary torsion, the Descemet circulation torsion, very bad. These are shell elements, and shell elements in the form of ruled surfaces, because being a ruled surface, you can have your straight tendons, but still shape your element. These were hyperbolic paraboloid, basically. And these are for waterproofing integrated elements. So these are the way in which, well, they started from Italian standards and we brought it to the European one. But as a matter of fact, this required some regular testing on elements. So we developed, we had Politecnico, or also, you know, Professor De Crisciano in a group of Professor Plizzari, University of Brescia. We developed some portable tools that can be brought to the factory, and you can test the element as such. This was a 15-meter long element, or you can see here, this is in a yard with this load redistributing, and we measured, you know, you see some LVDTs here to measure the elongation. And these are some images. This was a double T element. These are some images. This was tested in shear. You can see the diagonal cracks which formed here. This element here was without any shear reinforcement, just the tendons. And you can clearly see that there is this shift, relative shift. This here was with stirrups, with regular stirrups. And you can clearly see the strut and tie mechanism which is formed, because these two cracks clearly highlight the strut in the mechanism. This one here was with fibers. And the interesting was were 80 kilos per cubic meter of fiber. So it was a good fiber reinforced concrete. And the mechanism of failure shifted from shear towards shear flexure. You can see here that there is also, you know, there are several cracks, but also here you can see that there is some failure at the compression part, because it's going into the, you know, the flexural mechanism. Here you can see, this is an image of, these are the sketches of how did we put the steel bar bundle. So we started, you see, I can see here. The one was here, then we put 2 here, then we went with 3 and 4 here to symmetrize the loading, then we brought the 5th and the 6th and so on. And which was the purpose of doing these full-scale tests? Well, because, you know, when we design a reinforced concrete structural element, in most of the cases we have a rectangular cross-section. And for the rectangular cross-section, the Bernoulli beam model works perfectly. Planar cross-section assumption, and you go ahead. But in an element like this, can you guarantee planar cross-section assumption? This is made with very thin parts. So if you look here at this, you know, this figure here, this was an element similar to that. You see that we have here 1, 2, 3, 4, 5 LVDTs positioned at the different heights along this wing of the element to measure the deformation. The purpose of putting so many of them was exactly to check with the profile of the deformation if the planar cross-section assumption was true. And in this case, it was true, really close to the failure. So we could apply the beam model. Because if the planar cross-section assumption is not true, you apply the beam model, but you do not know if that model is okay. So testing the full-scale element was also to check if the response of the element and what we could predict, this is this black line or this thinner line according to different hypotheses that we made of the constitutive law, this is what you predict using the beam model. And we wanted to see whether an element with a shape like this could be designed according to the beam model. This is, you see those hyperbolic paraboloid, you see the shape at failure. This is a clear stability problem because the element came like a very flat arch. And when it starts deforming under load, at a certain point it becomes a three-hinged arch but loses the stability and collapse like that. But still, you could see on the bottom, at least until we were able to go underneath to mark the cracks, because from a certain point on you cannot go anymore because you realize that it's no longer so safe. But you can see that still there was a very good behavior because you have a very nicely distributed cracking, which is exactly what you want from this kind of elements. And well, an overview of, as I said, all started in Italy from the prefabrication of these beam elements for slabs. It was at least quite common to have this beam and block system, which was completed by a cast-in-place pouring, so that you have a T-beam formed by this precast element, the pour concrete, and the top slabs. And these clay blocks had a twofold purpose. First of all, to reduce the weight. But after that, they also have a minimum of sound and thermal insulation capacity. So, for example, you do not hear your neighbor up floor or down floor when he shouts and so on. And well, nowadays it's common that you do not have any more central heating. So if an apartment is heated and the other one is not, at least you compensate that. Then we went into hollow core slabs. Nowadays, for new construction, the most common form of slabs is either with precast elements or with this predal, in which you precast the bottom slabs, and there are these steel trusses, and these are polystyrene blocks which perform both the function of lessen the weight and provide some insulation, and we complete with some cast-in-place casting. An important thing, we will have a class on that, is, well, these elements have to be assembled to form a structure. You can have some cast-in-place completion, but you might not have also. When you do not have, you have typically steel connections. For example, these two pictures here, this is a rail. It's used in precast panels to handle them, to tie them to the beams. And we observed in earthquake, in a very severe earthquake we have about 15 years ago in Italy, that the weak point in precast buildings were exactly there. So designing the connection is absolutely fundamental. And there are a few more slides on, when we spoke about standardization. For example, hollow core slabs come in a limited number of, well, the width is generally fixed. It's 1.5 or 2.4, 1.2 or 2.4 meter because it's the width of the precast runway. But comes in a fixed number of depths with shapes. So you can really limit the number and go into standardized construction. These also are some, double T slabs. You see here you have a very, very thick bulb, which is generally when you need to guarantee some specific fire resistant requirements, that you need some more solid part and better cover. And these are some examples taken from the catalog of a precast producer, so shapes for columns, for roof beams, for floor beams, and for floor elements. Some examples of how do you see here there are some weighting reinforcement, which is for the connection of the floor elements to the beams. These are some of the issues that we are going to see. These are some multi-story building. You see, if you have to go higher, here is where you are going to connect the column of our top floor to the existing columns. You can see here some other things. Nowadays we use as a basic modules the 3 meters. So we have elements in the multiple of 3 meters. And this is the modules that we have used in our system. Another thing is, how do you deal when you have a shape like this? Actually, this is a building, I think it's somewhere in the UK, but this resembles the shape of a very famous building. Was the first skyscraper in Italy, which is in Milano. If you have ever been, when you go out of the station, is exactly on the right side, and it's where the regional council has its main offices there. It was designed, the Pirelli building was designed by Pierluigi Nervi, so famous engineer and architect. Can you imagine why this shape? Yeah, it's to make it resistant to the main wind directions. Yeah. But how can you cope with this building when you say the precast, we want standardized that, so we want rectangular and so on. So how can you cope? And this is an example of how the architect and the engineer solved the layout. So you can mainly have these precast slabs coming into a limited, so many of them were of the same size, so you have only to adapt for the very edges, and these are some examples of how it was solved. So there were some special elements you can see here which were not in the standardized side, because to produce a special element means that you need a dedicated formwork, but only for a limited number of elements, so it's not economically effective. But the other thing was that do not precast all. If you have to complete some regions, just complete with cast in place. The other thing is that oops, what did it happen? How? This, okay. Make construction details simple, because they must not only have been built, but the precast element must go through transient stages. You have to pick up this beam, you have to lift it up and put in the stocking yard, and put on the truck to transport, lift it, put back, put on, and so on. There are these transient stages. If the detailing is complicated, it can hinder, it can be an obstacle to this. And also consider that an element deforms under loadings. As we say, concrete is a living material. It shrinks and creeps. These deformations have to be taken account of. So, for example, never put a dry contact, concrete to concrete, because this first of all, brings very high friction. And there has been in the past some cases where this very high friction, this very high friction is a force applied at the interface between the beam and the column, not at the axis of the beam. So this force here has a bending moment with respect to the axis of the beam. It's a negative bending moment for which you may not have designed your beam. So you might have cracking on the top, or you might have excessive deflection. The other thing is that, dry to dry concrete, dry contact, concrete to concrete, dry contact, you have asperities and so on. You have to distribute your load, and you have also to accommodate for if the beam is simply supported, it means that its edges rotate. So you have to accommodate this rotation and avoid that when it rotates, the beam does not go to hit the corner of the column, because at that point, the force goes all through that corner and you chip it off. It's not a static problem, never will happen. But it's something that the owner can call and you make some repair. It's an aesthetic problem and so on. So these are issues that you have to take into account. And we have to take into account the construction tolerances. It's true that it's an industrial process, but we might have tolerances. And we also have tolerances, but also in the positioning, in the erection. These have to be taken into account. These are part of the design process that we have to consider. This is the same. This is the connection between a facade panel and a beam, for example, here. And you see that we have these steel devices which have some spaces, some slots to accommodate the position of the connecting bolts exactly for this, because you might need to position them, and you might also allow them to allow some movement because of shrinkage and creep. Otherwise, if concrete shrinks and you have two fixed connections, you have tensile forces in the element that you might not have designed for. This is an example of the connection system for columns, which was I was telling you with. You see, you might have bars coming out of the foundation slab, and your column is equipped. There are these we call column shoes that you use also to as a guiding to position your column correctly, and then you tight the bolts here. Or an alternative could be that instead of having the column shoes, you have some holes in the columns where you position that, and then you fill these holes, generally with shrinkage compensating growths. I think these are the very last slides, more or less. Another benefits that we can have is that, as we were saying before, the roof elements can come already with waterproofing already pre-installed. You install it in the factory, which means that you limit not only the operation on the site, but can you imagine that you have made this 10-meter tall building and the workers have to go to put the waterproofing and so on at 10-meter height. So you need special safety equipments to be installed and so on. Whereas if you do in the yard of the precast site, the worker is working at 60 centimeters and so on. And also there is a better quality control, because making a job at 10-meter high, it's different than making a job in the yard with quality control. This is in industrial buildings, but in residential buildings, you can bring floor elements which have already some piping, some ducts, some electricities and so on already installed. For example, hollow core slabs are naturally prone to this because they already have these cavities where you can accommodate, but you can also have these fixings already installed in the elements when it's prefabricated and bring a partially or quasi-finished element to the job site. And these are some images of the waterproof layer for these elements, or these are images of modules of an apartment building. This was a bathroom which comes with already all the equipment already installed and brings say 96 apartments in 96 days. You have to offset most of the work that you can do so that you limit the work on the site. And I think this was the last slide for this morning. So this was just to give you an overview of the main aspects and some of the topics which we are going to cover during the lecture of next days. So I think that our lunch is waiting for us now. Thank you.